My name is Yoshida. I will be presenting on the HBase and Kafka data pipeline and application for line messaging platform. This is today's agenda. First, I will introduce you to HBase and our use case at line messaging platform, and move on to today's main topic of HBase and Kafka data pipeline and its application. First, let me talk about HBase and our use case with line messaging platform. First, about myself. I joined Line as a new graduate in 2018, and I reside in the HBase unit within line messaging platform. What you see in this diagram is the technical stack of the line messaging platform on the server side. Line's server side is comprised of multiple server-side applications, and they are developed using Java and Spring. Each server-side application acts as Redis, HBase, and Kafka as data source. Our HBase unit is in charge of building and operating the HBase clusters that are used in server-side online messaging platform. And also we develop patch for HBase and contribute patch to AppStream. In addition to HBase cluster operation, we also build data access logic for HBase or develop storage deployments. HBase clusters depend on Hadoop or Zookeeper, so we also develop and operate such Hadoop clusters for Zookeeper clusters for HBase. For monitoring, we use Prometheus or Grafana, Elasticsearch, Kibana, and for provisioning, we use Ansible. I would like to briefly introduce you to what kind of data is stored on HBase. User information of the line messaging platform, user device information, and configuration information are stored. Also, the friend relationship among users and meta information such as a user chat information or groups, and the message sent and received by users. When a user receives messages, events such as send message or receive message, which we call talk operation, are generated, and these event information is stored on HBase cluster. I would like to briefly explain the HBase architecture. As I mentioned earlier, HBase depends on Hadoop or Zookeeper. HBase is made up of odd-numbered controller node and a worker node which spans to tens or hundreds of nodes. Zookeeper quorum in this diagram is the daemon for Zookeeper, and we run this on the controller node. Name node, journal node, and data node are Hadoop file system daemons, and the name node and journal node run on the controller node, and the data node runs on the worker node. With Hadoop file system, files are divided into multiple blocks and are stored on the data node. Each block is either 64 megabyte or 128 megabyte. We use 3 as the replication factor, meaning that the same block is stored on 3 data nodes. The name node manages which block is comprising the file and which worker node or data node each block is stored. HMaster and HRegionserver are daemons of HBase, and HMaster runs on controller node and RegionServer runs on the worker node. Region is a unit that horizontally divides HBase tables, and HMaster allocates each region to RegionServer. The client sends requests to the RegionServer that it's allocated to the region that responds to the data they want to access. Each region server accesses the block on the data node as needed and responds to the request from the client. Let's assume that a trouble took place on a worker node. Even in such a case, because of the 3 replicas, the blocks on the Hadoop system can still be accessed. Therefore, the region that was allocated to the region server that was on the node with the trouble is allocated to another region server and then continue responding to the request from the client. I would now like to briefly explain HBase internal write flow. Client will send a request to the region server that it is allocated with the region that responds to the data they want to write to. Region server that received the request will update memstore, which is the data store on the memory that exists for each region. And then it appends to the WAL file on HDFS and write ahead log files. Once the write on the WAL file is successful, the persistence of the data is deemed successful and responds to the client. If the write to WAL file fails, memstore is rolled back. Every time the memstore reaches a certain size or a certain time has elapsed, the contents of memstore is flushed using file format called H files on HDFS. Let's assume that a trouble happened with this region server A. In this case, the HMaster will reallocate the region 1 that was allocated to this region server A to another region server, which is region server B. As I mentioned earlier, the WAL files and H files on HDFS can still be accessed, but the contents of the memstore, which is the data store on memory, will be lost. So the region server B will read the WAL file of the region server A and restore the contents of region 1's memstore to the point right before the trouble. WAL file is used to ensure the reliability of the data. HBase has a cross-cluster replication function as a standard function. Here we assume that the replication from source cluster to destination cluster is set up and explain about this replication. If replication is set up on the source cluster, each region server initiates a thread called replication source. This replication source reads the WAL file on the HDFS and hands over each entry of the WAL file to ReplicationEndpoint. ReplicationEndpoint is provided in a pluggable manner, and the standard replication endpoint sends the WAL entry to each region server of the specified destination cluster. The region server on the destination cluster that receives a WAL entry completes the replication by replacing each WAL entry. There are cases where the sending of the request to region server on the destination cluster fails. In this case, the HBase client that is used by the replication endpoint has to retry logic, and also retry logic is deployed on the replication source. So the subjective WAL entry is handed over to the replication endpoint until the replication endpoint's process is successful. The replication source stores the location of the WAL entry that has succeeded the replication endpoint process at the end as replication offset on Zookeeper. Let's assume that a trouble happened on this region server A. In this case, the other region servers, in this example, the region server B, will receive the replication offset A on Zookeeper, and by restarting the replication process from there, this allows for the replication to be completed without losing any data. The setup of replication can be done using HBase Shell, which is the management tool of HBase. When using HBase shell, the setup can be done using add peer command. Here, the replication ID 1 and the destination cluster are specified. This replication is used to replicate the production cluster within Tokyo region to backup cluster and also to replicate to disaster recovery cluster in Tokyo region and Osaka region. I mentioned earlier that the replication endpoint is pluggable. I would like to explain this in a little more detail. Here we will consider the replication endpoint that output all WAL entries to log. In order to independently define pluggable replication endpoint, the class that inherits replication interface is defined, and the replication method is overridden. In this case, all the WAL entries are output to log. The return value of replication method is true if the replication process succeeds. In order to use this replication endpoint, the classes of this replication endpoint exist on the class path on the region server, and by using HBase shell's add pair command to specify the class name, you are able to switch the replication endpoint process. From here, I would like to go into the main topic of today and talk about HBase and Kafka pipeline. We built this pipeline in 2017. Here, I would like to first talk about the status in 2017 and the background to building this pipeline. In 2017, we were using HBase version 0.90.6 in the production cluster. And for statistical analysis, we set up replication in HBase cluster called stats cluster. This stats cluster was managed by another team. The version of HBase on this cluster was 0.94. The version 0.90.6 that we used was a version that was released in 2012 and was very old. And at the time of 2017, could no longer receive the support from the community. So in 2017, we were conducting migration to relatively newer version 1.2.5. The migration of a new cluster with the new version 1.2.5 was created, and the writes from the application server was done on both the old cluster and the new cluster. And by copying the data from the old cluster to the new cluster, the migration was done. In order to stop the writes to the old cluster and to enable continuation of statistical analysis, we needed to set up replication from the new cluster to the stats cluster. But unfortunately, due to incompatibility issue, the official replication of 1.2.5 did not support replication on 0.94. The reason why is because this is the HBase version and their release dates. The version 0.96 that was released in 2013 is called a singularity by the community, and the communication protocol was changed significantly. And with the version 1.0 that was released in 2015, API cleanup was done, and this prohibited the communication across versions. So the replication from the version 1.2.5 that we used to version 0.94 was not supported. We cannot replicate to the stats cluster, or we will not be able to complete the migration. We solved this replication issue by building a HBase and Kafka data pipeline. By using the pluggable replication endpoint function that I explained earlier, the replication endpoint with the independent definition sends the WAL entry to Kafka by using a unique protocol. The replayer that consumes the WAL entry from Kafka writes to the stats cluster by using the 0.96 HBase client and protocol. I would now like to briefly explain about Kafka. Kafka is an event streaming middleware that uses PubSub model. The producer that sends data to Kafka specifies a topic and sends data in key value format. Topic is separated into multiple units called partition, and the partition is determined by the key. The consumer that receives data from Kafka subscribes each partition and processes the data. From here, I would like to talk about the building blocks of the data pipeline that we built. First is a protocol used to send data to Kafka. It is defined uniquely using protocol buffer so that the replayer for HBase 0.94 does not rely on 1.2.5 client. The data structure that was defined are WAL metadata information. These are WAL entries and HLOG keys. In addition to that, data structure called cell, which shows the changes to HBase, is defined. These data structures are similar to the protocol used in 1.2.5. Replication endpoint that sends WAL entries to Kafka does unique definition, and the topic, which is the definition for Kafka, is determined by table name, prefix, and suffix. Key that is sent to Kafka specifies the encoded region name, which is the identifier region, and the low key for each cell. WAL is transformed into the protocol that was defined earlier, and it is sent to Kafka using these. This Kafka replication endpoint setup is done like this using HBase shell and add peer command. The class name of Kafka replication endpoint that was defined earlier is specified, and Kafka connection information and client information, and the prefix and the suffix of the topic name are specified. The replayer that sends data to HBase 0.94 cluster consumes WAL data from Kafka and transforms that WAL entry into 0.94 mutation. And by using the 0.94 library, it writes to the specified cluster. Our HBase and Kafka data pipeline is generally known as change data capture. The strength of a pipeline is that we are able to conduct the process based on database changes more easily. Also, HBase replication deployment due to Kafka can be done with high reliability. On the other hand, the points to be careful are because the process is done asynchronously, there's always possibility of delays. And at the timing of when changes take place, in order to access other data or column, aggregation may be needed on the consumer side, or there is a need to access a database as needed.
To understand the strength of our pipeline, let's consider the possibility of implementing a similar processes in an application server without using pipeline mechanism. In such case, after successfully writing into HBase, the information would be sent to Kafka in the server-side application. There are several concerns and problems about this method. First, we need to carefully check that we have added a path to Kafka for every write path in HBase. Also, if sending to Kafka failed, how the replication is implemented. What about the retry logic? We also need to worry about the impact to application due to retry. Also, one of the most difficult problems to solve is that it's possible not being able to send all HBase writes if the application server fails while sending data to Kafka or during the retry process. On the other hand, our pipeline mechanism easily solves all of these concerns and problems. First, to enable all HBase write path, this can be achieved by simply setting up peer replication, since the replication source will target all writes of the specified table for processing. Also, the handling of retry against Kafka is very reliable thanks to the Kafka client retry logic as well as those implemented in the replication source. We have also confirmed that Kafka failure for a short period will not have any performance impact on the service. And finally, regarding the reliability issue, we can store replication offsets on Zookeeper, and even if a region server fails, another region server will resume replication thanks to replication failover. All the HBase writes can be sent to Kafka even if the lead server fails. Now, let me share the examples of using pipeline of HBase and Kafka. We built this pipeline in 2017 and have developed several applications over the years since then. We have now applied this pipeline to more than 20 tables. At its daily peak, the pipeline is sending 1.2 million WAL entries per second to Kafka. Here are 4 use cases that have already been developed. The first is for replication and data migration. As I mentioned earlier, replication from 1.2.5 version to the 0.94 cluster is not supported by default. Also, replication from an HBase cluster without authentication to a secure HBase cluster with Kerberos authentication is not supported by default either. For such replication that is not supported by default, by implementing replayer, it is possible to replicate. It's also possible to replicate, migrate, and send data to other middleware and database other than HBase. Specifically, we are considering using such a pipeline to evaluate a relatively new database called TiDB with real data. The second example is a little closer to a service or application. We are developing a microservice called UserSettings. This UserSettings service is a microservice that manages settings for each user in the form of key values. We are opening up this service not only to the messaging platform, but also to other services within the company. Other services can send requests to the user settings service as needed to know the latest settings of the user. On the other hand, some services require additional processing to be performed when the user's settings are changed. We use the pipeline to satisfy these requirements. Send the WAL of the HBase user setting table to Kafka, and the consumer that consumes the WAL converts it into settings event, a data format that is easier for service and application to handle, and sends it to Kafka. By consuming this settings event, other services can implement processing in response to changes in user settings. The third use case is for near real-time statistical analysis. There are times of the year when a line bursts with 3 to 4 times the number of requests at the daily peak. This is the midnight of the new year. In Japan, it is known as the New Year's line, since everyone sends Happy New Year message causing bursts of requests at this time of the year. We are on high alert at this time every year and monitor a variety of metrics. One of the most important metrics is the message count. This is very important metric because the load on the various components increases in accordance with the message count. Therefore, there is a need to monitor the message count at a very high resolution and in near real time. Very high resolution refers to the time range such as every second or every 100 milliseconds. And near real time means that we can observe these accurate metrics within a delay of a few seconds. For the metrics of the message count, we utilize the pipeline. When a user sends a message, the application server stores the event send message in the HBase operation table. HBase operation table is sent to Kafka and run the consumer, which count the number of sent messages. Based on the timestamp of the sent message, this consumer counts the number of messages in the bucket of 100 milliseconds. The number is then sent to Elasticsearch, and we visualize it in Grafana. This is very interesting data, so let's take a look at the actual metrics. This is the number of sent message at 2021 New Year's Day. We can see that there is a burst of requests when countries such as Japan, Taiwan, and Thailand are celebrating the new year. Especially in Japan, we can see that the number of requests burst at 4 times at midnight 0000. Let's look at the detail for Japan. This is metrics from 11:59:50 to 000001, which we can see that 400,000 messages were sent at 000003. If you look at the time range of 100 milliseconds, it looks like this. These precise metrics are shared with the developers of delay of a few seconds. The fourth use case is app user detection. There are a variety of app users on the line messaging platform. We are detecting these app users from various perspectives. In particular, in terms of the persistent storage, HBase, the pattern of rogue app users that generate large amounts of data over a long period of time is critical. This is not just a disk usage issue, as it can have a very negative impact on the performance of the HBase. If the performance of the HBase deteriorates, it will affect a very large number of the users. We use pipelines to detect rogue users who generate large amounts of invalid data over a long period of time. We send the WALs of the table we want to detect to Kafka, and the consumer who consumes the WALs sends them to Kafka. Maybe the consumers who consumes the WAL counts the writes for each user in a time range of 1 minute, 1 day, or 2 weeks. Then unauthorized users are detected according to the penalty conditions stored in Central Dogma, a configuration repository developed by our company as OSS. The detected rogue users are reported to our internal penalty gateway component, which in turn reports the rogue users to our HBase cluster. The user's penalty will be stored in a table in our HBase cluster where the data such as user penalties are stored. Line's application server will then use this penalty information to block the request from the unauthorized users. We will continue to expand the use of this HBase and Kafka data pipeline in the future. Here, we will introduce the secondary index, also known as materialized view, and incremental backup. This is the use case we are thinking for the future, and let me explain. As for secondary index, HBase supports only ordinary indexes that look up values from keys such as row and column. For example, when Alice became friends with Bob, here we want to store a record on HBase with Alice as the key and Bob as the value. In this case, we can use Alice as the key and look up Bob, but we don't do a lookup of Bob with Alice. On the other hand, you may need a secondary index to look up a key from a value. Apache Phoenix is a middleware that implements SQL on an HBase and provides this secondary index as a part of functionality. But since Apache Phoenix is designed to implement SQL, it has overhead and may be overkill just for a secondary index. So we are using middleware like Redis and Cassandra for these secondary indices. On the other hand, we may want to implement a secondary index on the HBase for some reasons. We are considering the use of pipelines as an enabling technology to realize such secondary indices. Based on the data in the key value format, value is converted to key and written back on HBase. In this way, the application server can look up the key from the value. The actual implementation of such a function would be more complex, but we are considering using the pipeline for the elemental technology to enable such a function. Next is incremental backup. First of all, let's talk about incremental backup in HBase. HBase incremental backup starts by taking a full backup, a complete backup, and uploading it to storage such as HDFS or Amazon S3. Then incremental backup are taken periodically using cron job or other methods. Incremental backups are performed by MapReduce that reads the WAL file and converts it to an H file. This H file is then uploaded to the storage as an incremental backup. There are several pain points with this HBase standard incremental backups. First, the MapReduce job needs to be run, which may add extra load to the cluster. Also, while taking incremental backups, WAL file cannot be deleted and all WAL files remain on the cluster during the interval when cron job is starting. This may lead to data usage problem. There are also pain points in restoring from incremental backups. For example, in this case, a bug was released after T2, and the release of this bug caused damage to the data, let's suppose. So we want to go back to the point when the bug is released. In this scenario, you can restore the table from a full backup and backup of T1 and T2, but you will lose the data from T2 until the release of the bug. To solve these pain points, we are considering using pipeline. Here is how to take an incremental backup. The first step is to take a snapshot, which is a complete backup, and upload it to the storage. The consumer who is going to consume the WAL will then upload the WAL to the storage accordingly. At regular interval, WAL is converted to H file format for faster data recovery. By doing this, you will get an incremental backup, which will solve the pain point mentioned earlier. Consider the case of restore from these incremental backup. Let's suppose restoring right up to the point when this bug is released. In that case, we can restore the table from the full snapshot and incremental backups of T1 and T2 and replace the WAL from T2 until the bug is released, thus minimizing data loss and restoring the table. This is the end of our work on HBase and Kafka data pipelines and their use cases. We are leveraging these pipelines on the line messaging platform, and our pipelines are built using HBase mechanisms such as HBase WAL and replications. This pipeline is a very reliable and powerful method for processing based on changes in the database. I covered 4 real applications and 2 use cases that we are thinking in the future, how this change data capture can be used. I hope you will think about how you could use change data capture in your services. That completes my presentation. Thank you.